Are there physical laws that we will never be able to discover no matter how smart we get? That is the unsettling possibility raised by the undecidability of physics, a concept that connects deep mathematics with the limits of scientific knowledge. Gödel's incompleteness theorems showed that in any complex logical system, like mathematics, there will always be true statements that cannot be proven within the system itself. Now, physicists are asking, could the universe work the same way? Could there be natural laws or physical truths that are real, yet forever beyond our ability to prove or predict? How could this happen in physics? Many physical theories, especially in quantum mechanics, cosmology, and string theory, are built on complex mathematical frameworks. If Gödel's theorems apply here, it could mean that some aspects of reality are formally undecidable. No equation or experiment could ever fully resolve them. Example, in a theory with infinite possibilities, like certain multiverse models, some outcomes may be true, but not provable from within our own universe. Analogy, it is like trying to read a book that contains pages that rewrite themselves when you look away. You may never fully grasp the story. The undecidability of physics reminds us that even with perfect data and brilliant theories, some mysteries may remain fundamentally unreachable, not due to our ignorance, but due to the very nature of reality and logic itself. How can Gödel's incompleteness theorems, originally formulated for arithmetic, imply that there may be physical laws or predictions that in principle cannot be derived or disproven within any single consistent theoretical framework? Physics strives to encode the universe in mathematical axioms and equations, yet if those axioms are rich enough to encompass basic arithmetic, Gödel tells us they must harbor true statements that elude proof. This tension between the aspirations of a theory of everything and the inherent limitations of formal systems gives rise to the undecidability of physics paradox. So far, so good, until we realize that any candidate for a final physical theory must necessarily include the mathematics of integers and real numbers, making it subject to Gödel's first incompleteness theorem. Even if the theory is consistent, there will be propositions about physical quantities or behaviors that cannot be settled by its own axioms. In practice, this means that certain predictions, perhaps regarding the behavior of a quantum gravitational system or the outcome of a highly complex many-body interaction, could represent statements that are true in reality but unprovable within the theory itself. At its core, Gödel's second incompleteness theorem deepens the conundrum by showing that such a theory cannot even demonstrate its own consistency. If physicists could prove that their fundamental laws are free of contradictions, those very laws would contradict Gödel's result. Thus, the dream of a self-verifying, grand unified, or quantum gravity framework collides with an unavoidable blind spot. The theory might be inconsistent, or if consistent, incapable of proving that fact. Either way, there remain domains of physical inquiry that resist closure. Yet even this logical boundary is intertwined with computational considerations. Many dynamical systems, particularly those exhibiting chaos or defined on continuous fields, are known to encode Turing-complete behavior, meaning their long-term evolution can simulate arbitrary computations. Since the halting problem tells us we cannot in general predict whether an arbitrary computation will terminate, certain questions about a chaotic or computationally universal physical system may likewise be undecidable. We thus face scenarios in which no algorithm nor any deductive proof can settle whether, for example, a particular initial configuration eventually returns arbitrarily close to its starting point. And then there is the empirical facet. Measurements never achieve infinite precision, and noise can mask the very signatures of undecidable behavior. Even if a theoretical prediction is in principle undecidable, experimental verification might demand infinitely precise control over initial conditions, an impossibility in the real world. This blend of mathematical undecidability and practical measurement limits compounds the paradox, suggesting that some aspects of the universe could remain forever beyond both proof and empirical confirmation. In essence, the undecidability of physics paradox reminds us that the quest for complete contradiction-free depiction of nature may be thwarted not by lack of ingenuity, but by the fundamental structure of logic itself. Much like the hysteresis paradox reveals history-dependent surprises in macroscopic systems, and the deep-sea submersible failure shows the fragility of engineering under extreme conditions, Gödel's theorems expose an intrinsic ceiling on what our theories can ever prove, leaving room for mysteries that no amount of mathematical or experimental refinement can fully resolve. The Undecidability of Physics Paradox asks whether Gödel's incompleteness theorems imply that there are true physical laws that no finite theory can ever prove. Since physical theories are formulated in mathematics, any sufficiently powerful axiomatic system describing the universe may contain statements that are undecidable within that system. This suggests a fundamental limit on our ability to derive a complete theory of everything. Consequently, there may always remain aspects of nature that elude formal deduction. Attempts to encode quantum gravity in a single axiom set might leave some predictions forever beyond proof. It is like trying to compile an instruction manual that can never fully describe its own writing process. A formal system is complete if every true statement expressible in its language can be proved from its axioms. It is decidable if there is an algorithm to determine every statement's truth. Physical predictability, by contrast, demands that our mathematical models yield definite outcomes for all conceivable experiments. Gödel's theorems show that completeness and decidability cannot both hold in any rich enough formal system, raising the question of whether our physical laws can ever be fully predictive. Thus, absolute predictability may be mathematically unattainable. Even if we specify all initial conditions for a classical field, there might be questions about its evolution that no calculation can answer. It is like a puzzle set that contains pieces with hidden shapes. Some fits may be unknowable no matter how many rules you have. When we encode physical laws in mathematics, such as differential equations or Lagrangians, we implicitly choose an axiomatic system underpinning them. Gödel's first theorem tells us that any such system rich enough to include arithmetic will harbor true but unprovable propositions. In physics, these could correspond to statements about specific configurations or constants that the theory cannot decide. Therefore, the very process of formalizing nature introduces potential blind spots. A theory of discrete spacetime built on Peano arithmetic may be unable to prove certain combinatorial properties of its own structure. It is like building a map that cannot fully capture all the hidden paths in a labyrinth. Gödel's incompleteness arises because self-referential statements can assert their own unprovability, creating a logical gap. In physics, analogous self-referential can occur when a theory attempts to describe observers within itself, potentially leading to undecidable measurement outcomes. Such circular definitions can generate halting problem-like scenarios, where the theory cannot predict whether certain processes will ever terminate. This mechanism highlights how self-perception can break decidability. A universal quantum computer described entirely within quantum theory may face an undecidable "will this program halt?" question. It is like asking a library catalog to include itself. Some entries about the catalog cannot be cataloged. Physicists often extend or change axioms to resolve paradoxes or incorporate new phenomena, such as adding supersymmetry or extra dimensions. However, each extension creates a richer system, potentially subject to fresh, undecidable propositions. No finite chain of axiomatic extensions can guarantee closure against all future undecidability. Thus, the search for a final self-contained axiomatic basis for physics may be endless. Extending general relativity with loop quantum corrections addresses singularities, but may introduce new formal gaps. It is like patching software bugs by adding new code, only to find fresh bugs in the expanded program. The dream of a theory of everything presumes a complete and decidable foundation for physics. If undecidability is intrinsic, then any candidate theory may leave some questions unanswered or unanswerable. This imposes a fundamental limit on predictive power. There will always be physical questions that no amount of calculation can settle. Accepting this limit reframes our scientific goals from ultimate completeness to practical understanding. Even a unified field theory might be unable to predict certain particle masses without experimental input. It is like knowing the complete code of a video game but not being able to predict every possible emergent glitch. Undecidable aspects of theories can manifest as experimental anomalies that no model can account for. Scientists might encounter reproducible phenomena that resist theoretical explanation, revealing the boundary of formal predictability. Acknowledging this possibility shifts emphasis toward empirical phenomenology and the development of approximate or probabilistic models. It recognizes that measurement itself may transcend formal proof. Persistent quantum anomalies might signal theoretical propositions that lie beyond proof within quantum field theory. It is like encountering optical illusions that no amount of planar geometry can fully explain. Simulating systems governed by undecidable dynamics risks non-termination or unpredictable algorithmic behavior. akin to the halting problem in computation. Numerical methods may fail to converge for certain parameter regimes, reflecting deep formal limitations. Identifying which classes of physical problems are provably decidable remains a major challenge. Overcoming or circumventing these hurdles requires new mathematical frameworks or heuristic approaches. Simulations of turbulent flows can become intractable, possibly due to underlying undecidable structures in the Navier-Stokes equations. It is like running a program that sometimes loops forever without ever yielding an output. Exploring the intersection of theoretical physics and mathematical logic may reveal which physical questions are inherently undecidable. Development of meta-theories or probabilistic logic systems might offer ways to handle undecidable cases pragmatically. Philosophical inquiry into the nature of scientific explanation will also play a crucial role. Ultimately, accepting undecidability could lead to a richer, more nuanced view of what it means to know the laws of nature. Research into category theory and homotopy type theory may provide alternative foundations less prone to classical incompleteness. It is like accepting that some horizons may forever lie beyond view, inspiring explorers to devise new ways of navigating uncertainty.